Let x1 and x2 be independent and identically distributed random variables with uniform distribution between 0 and 1. Y is the minimum of x1, x2, z is the maximum. What's the probability of y being greater than or equal to some value y? Given that z is less than or equal to some value z for any yz between 0 and 1. What's the correlation between y and z? So let's try and visualize this first. We have two random variables x1 and x2 uniformly distributed. So we can show them on two axes here, x1 along this side, x2 along this side, between 0 and 1. We are given that z is a random variable which is the maximum of x1 and x2 and z is less than or equal to some value z between 0 and 1. So we show z on both of these axes as a point between 0 and 1. The probability that z less than or equal to z would be the area of this square, which would be z square. Similarly, we also show y along both of these axes here. Now the probability that y is greater than or equal to y and z less than or equal to z would be this yellow area over here. And we had to find what's the probability of y being greater than or equal to y given that z is less than or equal to z. So this would be probability that y is greater than or equal to y and z less than or equal to z divided by the probability that z is less than or equal to z. So as we have just seen, the probability that y greater than or equal to y and z less than or equal to z is the yellow area over here, and the probability that z is less than or equal to z is z square. So we have this probability z minus y square divided by z square. So this is the answer to the first part of the question. Probability of y being greater than or equal to y given that z less than or equal to z is z minus y whole square divided by z square. Provided that y is less than z, because if y exceeds z, the common area would be 0. So the probability would be 0. For the second part of the question, we have to find what's the correlation between y and z. So we can write the correlations as the covariance divided by the product of the standard deviations. And we know that the covariance is equal to the expected value of the product minus expected value of y times expected value of z. And the standard deviation is the square root of variance. Variance can also be written in terms of the expectation as expected value of y square minus expected value of y whole square. So now we have to find all of these expectations and plug in the value to find the correlation. And to find the expectation, we need to find the PDF of the distributions. So that's what we'll do first. A common approach to find the PDF is to first find the CDF of the distribution and differentiate it to find the PDF. We know that the CDF of a uniform distribution between 0 and 1 is given by this: fx equal to x minus a over b minus a, where x is between a and b. In our question, a and b are 0 and 1 respectively. So if you plug in a as 0 and b as 1, we will get fx is equal to x for x between 0 and 1 and fx equal to 1 for x greater than 1. Now we have to find what's the PDF of y and z, where y is the minimum of x1 and x2 and z is the maximum of x1 x2. But let's find it for a general case of n random variables, and then in the end we'll put n equal to 2 to find the values for our question. The CDF is defined as the probability that the random variable is less than or equal to x. Now since we are solving for a general case, z is the maximum of the n uniform random variables. So we replace zn with maximum of x1 x2 till xn is less than or equal to n. If the maximum of x1 x2 up till n is less than or equal to n, it means that each of x1 x2 is less than or equal to n. So we replace maximum x1 x2 with x1 is less than or equal to n and x2 less than or equal to n up till xn is less than or equal to n. And each of these random variables are independent, so we can write this as probability x1 less than or equal to n times probability x2 less than or equal to n up till probability xn less than or equal to n. Now this is the CDF which is fx equal to x as we just saw. So we can write each of these as x, so the product becomes x to the power n. So now we have the CDF x to the power n. We can differentiate it with respect to x to get the PDF, which becomes n times x to the power n minus 1. And using the definition of expected value, x times f of x dx, and we integrate it from 0 to 1, we get the expected value of Zn equal to n over n plus 1. Using the exact same approach, we can find the PDF and CDF of y, which turn out to be 1 minus x to the power n, and the PDF is n times 1 minus x to the power n minus 1. And in the same manner, we find the expected value of y, which is the integral of x f of x dx from 0 to 1. This turns out to be 1 over n plus 1. In our question, we have two random variables, that is n is equal to 2. So we can substitute n is equal to 2 in these expected values to get the expected value of our random variables. So expected value of z turns out to be 2 by 3 and y is 1 by 3. Similarly, we put n is equal to 2 in the PDF functions which we just calculated. So the PDF of y is 2 times 1 minus x, and PDF of z is 2x. Now we can calculate the expected value of y square, x square f of x dx, and then integrate it from 0 to 1. This gives us the expected value of y square equal to 1 by 6. And the expected value of z square x square f of x dx integrated from 0 to 1. This gives us 2 by 4. So now we have expected value of y, and we have expected value of y square, expected value of z, and expected value of z square. So we can calculate the variance of y and z using this formula: expected value of y square minus expected value of y whole square, and expected value of z square minus expected value of z whole square. Both of these turn out to be 1 by 18. And in case you're wondering if it's a coincidence that both of these variances are equal, it's not. The variance being equal, that this will hold true for all n. Now we need to find what's the expected value of yz. For this, we'll need the joint PDF of y and z. So we'll follow the same approach. First we'll find the CDF, and then differentiate it, find the PDF. So the CDF of yz is probably that y is less than equal to y intersection z is less than equal to z. So I can write this probability that y is less than equal to y intersection z less than equal to z as probability z less than equal to z minus probability y is greater than y intersection z less than equal to z. If you recall this initial figure which we had, the area which we are talking about for the joint PDF would be the area of this blue region. That's because from the total area z square, we have to subtract the area where y is exceeding y, which is this yellow square. So that would be z square minus z minus y whole square. So we now have the joint CDF of y and z equal to z square minus z minus y whole square. We can now differentiate it with respect to y and z to get the PDF of joint PDF of y and z. Differentiating this CDF with respect to y and z, we get the PDF equal to 2. We put this PDF into the expectation formula and then integrate it from 0 to z and then 0 to 1. There would be two limits. There's a typo here, sorry about that. We get the expected value equal to 1 by 4. So now we have all the required expected values in this expression to find the correlation. We put in all the values and we get the final answer of the correlation between y and z equal to 1 by 2. And this is the answer to the second part of the question.